All right there, young students of chemistry. Before you begin with this quick little presentation, you're going to need your periodic table, if you have not memorized them, your list of strong acids and strong bases. You're going to need a calculator, and this note sheet that corresponds with what I'm doing on the board, which is called acid-base mixture problems. Okay, so you learned at the beginning of the unit that the way we define a strong acid is that it ionizes completely. The entire amount of moles of the acid turns into hydronium ion. And we know that for weak acids, that is not the case. So when we mix a strong acid with a weak acid, the weak acid really is not a good contributor of hydronium. The amount of hydronium that it will contribute to the mixture is so little compared to the amount that the strong acid is going to add to the mixture that we just ignore it. So if we're going to solve for the pH, and that's what we're doing in these problems, solving for pH of a strong acid mixed with a weak acid, we're going to get the moles of hydronium from the strong acid only. And then adding the weak acid to the strong acid is almost like diluting that acid with water. So then to get the concentration of hydronium, we'll divide by the total volume. And that's going to give us, because it's an acid, and we know that acids make hydronium, that's going to give us the hydronium concentration. And then, of course, pH equals the opposite of the logarithm of hydronium concentration. So if you think in the terms of strong acids, and strong bases, weak bases, it makes sense that if we're going to, I'm skipping down one here, if we're going to mix a strong base with a weak base, wouldn't we follow through with the same procedure for calculating concentration? We would get moles of this time, because bases make hydroxide, we would get moles of hydroxide from our strong base only, and then divide by the total volume. So hydroxide concentration this time is equal moles of hydroxide from the strong base. Please remember that if it is a family 2 strong base, you're going to have to double the concentration of the base to get the moles of hydroxide. And then we'll divide by the total volume. And since we're dealing with a base and it's making hydroxide, to get pH, we'll do 14 minus the pOH, and pOH is the opposite of the logarithm of the concentration of hydroxide. Kind of following through logically, if we're going to mix a strong acid with a strong acid, both of those solutions are contributing hydronium. So we're going to get moles, because it's an acid, we'll be solving for hydronium concentration. Remember that if you see H+, H3O+, and H+ are often used synonymously. So you're going to get moles of hydronium from both, and divide by the total volume. To get the concentration. And then, of course, because it's an acid, pH equals opposite of the logarithm of this new concentration of hydronium. Same thing would follow through with the base, except this time, of course, we're making hydroxide. So if we have the mixture of 2 strong bases, we're going to do moles of hydroxide from both, divide by the total volume, and then, of course, the opposite of the logarithm of hydroxide is the pOH. So in order to get pH, we'll do again 14 minus the pOH, negative log of hydroxide concentration. Now, this last mixture, when an acid is in contact with a base, they react. We call that neutralization. So when we're reacting a strong acid with a strong base, it's going to make a salt that has a neutral nature. So the pH you would expect to be 7. So really, strong acid and strong base mixture, the pH will be 7 unless we have one of the reactants left over. We might have extra strong acid or extra strong base. So in this problem, we're going to have to react the acid and the base, and then we're going to have to determine the limiting reagent. Welcome back, my friend, the limiting reagent. And then whatever is left over after reaction will determine the pH of the solution. So we'll react the acid and the base. Of course, according to their mole ratios. Write the reaction. Do your before, during, and after reaction chart. The limiting reagent, whichever one it is, goes to 0. I'm going to say here for this case it's the base. And then whatever is left over here for the acid, we'll take moles of leftover and divide by the total volume of the solution. Remember, acid-base reactions occur in solution. And then we will follow through accordingly. This is going to give us concentration of something, either hydronium or hydroxide. If we're using my little example here, of course it will be hydronium because the acid is what's left over. And then we'll figure out what we need to do. Okay, I'm going to do 3 problems with you really quick, and then you have the back of the sheet to finish up. All right, the first thing you have to do when you're approaching these is determine what you have. So sodium hydroxide is a strong base. Strong bases are hydroxides of family 1 and 2. Aluminum hydroxide is a weak base. So knowing that the strong is the major contributor of hydroxide or hydronium, in this case hydroxide, we'll get moles of hydroxide from the strong only. And we'll do that by multiplying the volume by the concentration. So 10 milliliters times 0.2, I'm going to go millimoles, why not, per milliliter. That's going to give us 2 millimoles. Of hydroxide ion. And now we'll divide by the total volume. 10 plus 15 is 25 milliliters. Since we know that this is a hydroxide concentration, pH will equal 14 minus the opposite of the logarithm of 2 divided by 25. I dropped off the unit there, but I'm going to keep my significant figures. Those are important. And then you can just chug that out in your calculator using the appropriate keys. We're getting a pH of 12.90. You should ask yourself, hey, does my pH make sense? We're dealing with bases. The pH should be greater than 7. We have 2 significant digits in our concentrations, which means our pH is going to need 2 decimal places. So that pH is 12.90. In the next example, HNO3, it starts with an H, so we know it's an acid. You know from your steel trap, because you're going to memorize those 6 strong acids, that nitric acid is indeed a strong acid. Hydrochloric acid is also a strong acid. So in this case, we're going to get moles of each of hydronium from each of those strong acids, and then we're going to divide by the total volume. So 10 times 0.2 we've already discussed is 2 millimoles. 15 times 0.5 is 7.5 millimoles. 2 significant digits because of the concentration. These are acids, so the concentration that we are acquiring here is the concentration of hydronium. 2 plus 7.5 is 9.5 millimoles of hydronium divided by the total volume, 25 milliliters. And then we can get pH is equal to the opposite of the logarithm of hydronium concentration, which is 9.5 over 25. We have a very acidic pH of 0.42. Two significant figures in the concentration, 2 decimal places in the pH. Okay, and the last one. We have sodium hydroxide, which is a strong base. Start by identifying what your substances are by classifying them. Hydrochloric acid is a strong acid. We know that acids and bases react with each other. So hydrochloric acid plus sodium hydroxide, that's going to yield the salt sodium chloride and some water. We know that sodium chloride, because it has strong parents, is a neutral salt. So our pH is going to be determined by whatever it is that we have left over here. Again, we have 2 millimoles of sodium hydroxide, and we have 7.5 millimoles of our acid. So before reaction, sodium hydroxide was 2 millimoles. Hydrochloric acid was 7.5 millimoles. Determine the limiting reagent by dividing those moles by their coefficients. It's 1 to 1, makes it nice and easy. So we clearly know that the sodium hydroxide is going to run out first. So this goes down by 2 millimoles. Hydrochloric acid goes down by 2 millimoles times the mole ratio, 1 over 1. Even if it's a 1 to 1 mole ratio, you need to show me your mole ratio. 5.5. So after the reaction, we have some salt, a neutral salt, and we have some water, and we have 5.5 millimoles of hydrochloric acid left over. So we know that we're going to solve for the concentration of hydronium. Hydronium concentration equals 5.5 millimoles of hydronium from our strong acid, divided by the total volume. 10 plus 15 is 25 milliliters. So pH is equal to the opposite of the logarithm of 5.5 over 25.0. When you're doing that, I don't mind if you drop the units on the number you're taking the logarithm of, but please do not drop your significant digits. And we're getting a pH with two significant figures in our concentration. We need 2 decimal places. The pH of 0.66, which makes sense. What did we have left over? It was an acid, a strong acid, and it's pretty concentrated at 5.5 millimoles. All right, ladies and gentlemen, this is how we will be solving pH of acid-base mixtures. Remember, in this unit, we are focusing on pH of strong acids and strong bases only. Next unit, we'll hit the weak. Okay, happy calculating.